as guided by Engineer Okulo, I think the point here is we're just going to concentrate on the deck loading and analysis. Of course, we can include the issue of expansion joints and also the issue on bearings, just to give us an insight. So I think what we need, I prepared a small guide here. Practitioner's guidance note. So the bridge deck form. So I've already posted a lot of the deck configuration to you guys to appreciate. So you just look at for reinforced concrete T or I gather, we can look at reinforced concrete without precasting within up to 15 meters. Then beyond that you can do precast. Then also steel concrete composite. So we already shared some textbooks and he's going to share tomorrow more. So look at the deck configurations, look at the load models, analysis method, and the design. So the issue of carriageway, the notional lane, there is also volume 7 of road, I think road design manual, volume 7, I think it also talks about the bridge width, the notional lane, the carriageway, and then that volume 4 of bridge and road design manual. Try to look at it. It also has something. So just look at the different deck. You can do the normal forms, the different loads like the wearing surface, the raised walkways. You have the parapets of different kind, can be cross barrier or the normal steel post railing. Then any services that we expect to be on the bridge deck. Then the expansion joint determinations. That means the temperature loading need to be known. Since we are talking about the precast system, so that issue of creep and shrinkage will need to come off clear. We look at that. I know the software has, but engineer insists we also need to see where they are, the literature. So what the deck does, basically the golden rule is that the deck performs 2 structural jobs at once. Analyze one and forget the other, and the design is unsafe. So you have to be careful. The slab, that's under job 1. Then job 2, you have the flange. So the plate that carries wheel load directly and spans transversely between the beams governs local slab bending, reinforcement, and cover. So normally we call it, we do that like local effect analysis. So like you have we see the method of design, but local effect analysis now transversely. Well, while the bridge is spanning between 2 abutments or abutment and pier, globally, locally the wheel loads are being transferred from gather to gather through the slab, which is the bracing at the top. So that's why he's saying you design one, forget one, then the design is unsafe. So job 1 is the slab. Then job 2, so the beams, the girders become the support to the slabs. So you need to know that. Then job 2 is the flange, the top flange of the longitudinal beams, stroke girders, spanning between the supports, govern global bending, load distribution, and section design. Sometimes we feel nice to say global effect analysis, while here is the local effect analysis. So follow the load path from the wheel, deck slab to beam, girders, bearing, and substructure, as simple as that. Then the issue of deck form and configuration. Now we are looking at the reinforced concrete T-beams, beam and slab deck. Longitudinal reinforced concrete beam cast monolithically with the top slab. But also remember, sometimes you have precast. You have the beams design, non-composite with the deck slab, and the slab could be bearing on that. So you need also to be mindful, but in most cases our practice is monolithic or integral. So the longitudinal reinforced concrete beam cast monolithically with the top slab. In section, each beam and each share of slab forms a T-slab, we call it flange, that is compression web, the stem, shear plus tension steel. So economic span For the deck RCT beam, you have 10 to 25 for simply supported in situ precast post tension. This PT would have been post tension extends this. Definitely we are not moving to post tension. Then the beam spacing normally between 1.8 to 3, but in most cases even 1 you can do, 1.2, 1.5 depending, but I think even 1.5 we have registered girder spacing of 1.5, at least that I've seen here they are giving. So close up spacing reduces up moments. So we shall also look at deck optimization. I think currently one of the students from Makere is carrying out what we call deck optimization, depending on a different girder spacing. Then the slab thicknesses also vary depending on the spacing of the girders. Please note that when you are designing the issue of fatigue,
the packet.
You have also the slab. So here is giving you 200 to 250, governed by wheel bending cover minimum rules. Yeah, but the minimum, if you read the literature, the minimum is 225. Then goes up to about 300, depending on the spacing between the girders. Then the diaphragms are support and mid support, or the mid or third points distribute load transversely, and it is critical, or they are critical during construction. To control lateral torsional buckling of bridges, the girders can easily get off. So you have the cantilever slab, overhang carries parapet, footway and edgeway. Then best suited to short, medium span, in situ build, durable and robust. So trade-off here, heavy, high dead load and labor intensive to form, but low maintenance and forgiving. We have steel concrete composite deck, steel girders plus RC slab joined by shear connector studs. So they act as one section. Concrete takes compression, steel take neutral axis, and steel take tension. Neutral axis rises into the slab. Efficient use of both. Economic 20 to 100 plus for continuous plate girders. Definitely for steel composite, you have both the steel roll section, which goes up to about 20 to 25 roll section, then beyond which you can do plates. The flanges are all connected using welds, and the web, and the use also what we call the bearing stiffeners and the sips and intermediate stiffeners. We have multi-girder at 3 to 4 meter or twin girder with cross girders. You have seen, I've been posting certain section. The deck stuff vary between 200 to 300. Cast in situ on permanent form or precast, but definitely some. If you have haunches, then definitely here will be more. And even here, normally we also have from 2.5, depending on your deck width and how you are. So shear connectors are here. You also design for it. Headed studs transfer interface shear flow between the concrete and the steel beam. Bracing, cross frames and plan bracing resist LTB, that's lateral torsional buckling, distribute loads. Best suited to longer span, fast erections, silo design, lightweight, and prop construction. Watch the non-composite construction stage, fatigue of studs and welds and corrosion. So when you are preparing, when you are reading, these are some of the areas you just need to have interest. I think there's something on connection which I share. Then when you look at the RCT beam versus composite at a glance, aspect of economic span 10 to 25, 20 to 100. Self-weight high, low. Construction depth deeper, shallower. Erection speed slower, here is faster. So they are giving you the comparative analysis, but definitely every design you do, depending on the location, sometimes the location favors the composite than the RC, and therefore definitely you have to go for it. In most cases, in flat terrain and easily accessible areas, you are better off using concrete, and there are other benefits. So you can see all here. Then loads on the deck. Establish the loads before choosing the method. magnitudes come from the governing code. You can use ASHITO, EN, IRC, BS. The categories are universal. Permanent, they are here. Traffic are here. Environment, they are here. Accidental, construction, combined. All that you need to at least read and get some knowledge about. Also, on construction density, the material density is where you can generate the load from. All you need to read. Then you have the loads on the deck. You have traffic load models by code, so they're all here. And when you're going to design using manual, then definitely the way we may not do rolling loads. All these loads are translated into static, and then you use it to design. Simplified, especially for simply supported. They are here, and then pitfalls that catch newcomers out. Impact factor, tracked tandem, not the lane UDL or deadbolt. You have multiple presence reduction when several lanes load together. I think this one is more into the HAHB when the lane goes past 2. There are those reduction factors. When you are reading, you're going to see it there. Then local single wheel governs the slab, whose vehicles govern the girders. Include footway and parapet load for H-beams and conditions. Read everything. That's why you talk about raised walkways, and the services along the raised walkways and the parapets. Those are the loads that come at the edge of the slab. Loads on the deck. Don't skip the construction stage. Very important. Both construction. The steel composite also has 2 stages, and then also reinforced concrete precast section or precast members also have construction stages, unless you are doing reinforced concrete on props. So before the concrete add-ins, the bare steel girders alone carry the weight concrete, formwork, and plan, and also including the construction loading. Lateral torsional buckling and precamber are often governed by this stage, not the finished condition. Always run a separate non-composite analysis. Very important. Now, I've seen some of you are now designing 20 meter span and you are going in for composite approach. Therefore, now the good thing the software does for you, the non-composite and the composite. Now, the engineer is saying he wants you to do it by hand, manually. So you should be able to generate the loads that you apply on the precast girders, the analysis, and then from there get that is the section properties derived from that bare section, that girder without the top slab. Now, as soon as we cast the slab and the concrete hardens, then now you have additional, so you have a composite. So the section property becomes global. The whole of it be the deck slab and the girder itself. So you have improved and enhanced capacity. So which now takes the concrete weight or dead weight plus any other loads, including the live loads from the traffic. Composite, apply wet concrete self-weight to the steel only. Checked LTP, girder stresses, deflection, camber before composite action. While for the RCT beam, false work and formwork loading plus bulk sequence, premature depropping can overstress a partially cured concrete. Be careful there. So you need ample time. Method of analysis, you're going to see you have quite a number. You have a distribution factor or girder line, the influence line method. You have an analyze one girder for its share of load using code factors, faster and transparent. Relational analogy, the 2D mesh, longitudinal members, girder, slab, diaphragm, workhorse. Most beam and this self-composite moderate steel. Then orthotropic plate, finite element. Some of this may not be done, but at least it's good to know the different type. Then you also look at local slab and composite specific checks. For local slab analysis, effective width strip method, wheel patch carried by a slab strip spanning between beams. Influence surface, pusher or Westergaard patch loads. There's some charts I shared, read about Westergaard or pusher charts. yield line or plastic method for ultimate limit state and cantilever capacity. Look at the finite element plate models where geometry is irregular, cantilevers, so some of these, they are good if you are using your maybe some software and you can model from first principle. Then composite specific, effective flowing width, allow for shear lag, modular shear and transform section sort versus long term for group. So these are some of the things that you need to look at. Choosing a method, a practical ladder, preliminary sizing, regular depth, distribution factor or gather line, regular or moderately skewed beam and slab or composite. You do grillage analogy, sharp skew, curvature, variable depth, box cellular, do finite element, shell plus beam. Then slab wheel load design, any depth, effective width, stroke, influence surface, finite element if irregular. Rule of thumb, use the simplest method that is honest enough for the job. Justify anything more complex than grillage. So design workflow is here. Define geometry and form. List all the loads. Choose the method. Build a global model. Run construction stage. Run in service cases. Local slab analysis. Then you come to combine and check. Ultimate serviceability, all that. Strength, deflection, crack, fatigue. Then you have design details, stats, reinforcement, bearings, diaphragms, expansion. Then finally, check and verify. This is a practical design workflow. Common pitfalls to avoid. You are forgetting the non-composite construction stage, the number one composite error. Then using full slab width as effective flange, ignoring shear lag. So it's good to spend some time to get the effective, not full. Sometimes we make that mistake. Personally, also sometimes I just get the actual, which is not very good. But then applying the impact factor to the lane UDL or to dead load. Impact factor normally applies to Ashito loading traffic, but for BS 5400 they say the loads already include the impact factor, so if you do will be over design. Using force applying the impact and neglecting temperature gradient and shrinkage creep. This one normally that's the mistake, but at least now we have to do it. It's very important, because if not, there's the additional forces that arise from temperature, shrinkage, and creep. Undermodeling skew with simple distribution factors, ignoring cantilevers for parapet collision loads on edge members, and trusting a black box FE model without an calculation of benefit. This is exactly what AC is trying to counter. We must be able to have some tailor-made design, code reference design to counter check the software. Key takeaways: understanding bits numbers. The deck does two jobs. It is both the transverse slab and the gather frame. Check both always. Loads before methods. Fix the governing code and every load case first. Construction stage included. Simplest honest method. Gather line, grillage, FE, escalate only when geometry demands it. Composite needs stages. Effective width, modular ratio, shear flow, fatigue, and bare steel stage. Please check. There's when they gather act alone, and there's when they act in composite action. So always be aware. Now define your numbers. Follow the load path. Sanity check every model with a hand calculation. Codes give you the numbers. Judgment tells you how to place, combine, and interpret them. I think these are few snapshots that should be able to guide you when you're preparing for your deck loading and analysis. Yep.